In this video, we are going to look at the Jacobian matrix. But before we can look some couples of examples about Jacobian matrix, I will first explain using certain number of equations on how they can be represented in a form of a Jacobian matrix. So let me say now I have the following equations. Call this one y1 is given by x1 plus x2 plus x3 plus up to xn. Then I also have y2 given by x1 plus x2 plus x3 plus up to xn. And then I also have y3 is given by x1, x2, x3 up to xn. So if I want to represent this information in a form of a Jacobian matrix, this is how we go about. J is used to denote Jacobian matrix. So I will have the following. So in the first column or in the first row, it means I'm going to find the derivative of y1 with respect to x1. And then in the second column, I will have the derivative of y1 with respect to x2. In the third column, we will have the derivative of y1 with respect to the derivative x3. Then this will proceed up to n value, and then this, which means now we must have the derivative of y1 with respect to xn, where n can be any number of which the equation can run up to. And then in the second row, we are going to have the derivative of y2 with respect to x1 in the first column, and then in the second column we must have the derivative of y2 with respect to x2, and then in the third column it means we'll have the derivative of y2 with respect to x3. This will run up to the derivative of y2 up to xn. And then in the third row, it means now we'll have the derivative of y3, this is our y3, with respect to x1. Then the second column, we have the derivative of y3 with respect to x2. And then in the third column, we have the derivative of y3 with respect to x3. This can go up to the derivative of y3 up to xn. Also here we can have the derivative of yn, because the equations can be of any number, so it means we'll have the derivative of xn like this. Also here we'll have the derivative of yn over xn. The same thing will count on the derivative of yn over xn. Then even here we are going to have the same thing, the derivative of yn up to xn. So this information is used to generalize the Jacobian matrix. So since now we have generalized the Jacobian matrix, let me take you through some examples. So let me say now we have the following mapping. find the Jacobian of the following transformation. We are given that x is nothing but uv and y is given by u squared plus v squared. We want to represent this information in the form of a Jacobian matrix. So first, we've said that we must find J such that the derivative of x and y over the derivative of u and v can be represented in the form of a matrix. We've said that in the first row, the first column, we must have the derivative of the first function, and our first function is x with respect to the first variable. Our first variable is u, so it means we must have du. And then now in the second column, we will have the derivative of the first function x with respect to v. And then in the second row, we will have the differentiation of y with respect to u. And then in the second column, it means now we'll have the derivative of y with respect to v. Once now we represented this information in the form of matrix, we can now go direct into the main equations and differentiate them with respect to every variable of which we have to find. So now we have to find dx du, of which it will be our first entry into the matrix of column 1, row 1. Dx du can be found from x. This is our x, and then we differentiate x with respect to u. So it means we'll just have a v like that. And then now we can also find the dx dv. And then when we want dx dv, this is our dx equation. So we can differentiate this equation now with respect to v. It will just give us a u. And then these two entries are the entries of the first row. Then in the second row, it will have dy du, and then dy du, this is the equation for y. Then when we differentiate this equation with respect to u, we get 2u. Now v is a constant, therefore the derivative of v as a constant, it will be a 0, so we don't consider it. Then we go to dy dv. From this equation, when we differentiate it with respect to v, we will have 2v like this. Then we come and replace the variables inside the matrix by what we have here. So dx du is the same as v, so we write v. Dx dv is the same as u. Then this is our u. Now when we look at, we have dy du. Yeah, dy du, we have dy du is a 2u like this. And then our last entry is dy dv is 2v. So this is our Jacobian matrix. Then out of this matrix, we can also find the determinant. When you want the determinant, this is a square matrix, so you want to find the determinant of the Jacobian matrix. So you know how to find the determinant. Then this is u times 2v. This is v, not u. Then this is v. So it means we're going to have 2v squared minus u multiplied by 2u. then this is 2u squared. So now this is our determinant of the first Jacobian matrix. We can also look at another example for the sake of practice. So let me say now we want to find the Jacobian of the following transformation, where we are given x as u squared minus v squared and y is nothing but u squared plus v squared. We want to find the Jacobian matrix of the following transformation. J is given by the derivative of x and y divided by the derivative of u and v, because u and v are two variables from our main functions. Then this is nothing but can be represented in this matrix. Then in the first entry we're going to find the derivative of x with respect to u. Then here we'll have the derivative of x with respect to v. Then in the second row we'll have dy, du. Then the last entry is dy, dv. Then from now on is a matter of differentiating what we have, and then dx, du, so can be found from this equation. When differentiated with respect to u, this is just 2u like this, and then we go to dx dv, dx dv. Then dx dv, we differentiate the same equation as now with respect to v. It means we'll have minus 2v. And then again we also have to find the dy du, dy du. Then dy du will be found from this equation. When we differentiate this equation now with respect to u, this is 2u. V squared is just a 0 because now we treat it as a constant. So now we find dy dv. We differentiate this equation with respect to v. It's nothing but 2v. So when we're at this point, it means now we can represent this information in the form of our Jacobian matrix. So J is equal to the differentiation of x and y over the differentiation of uv. uv is given by the following matrix. So in space of dx du, we are going to write 2u in space of dx dv. It means now we have minus 2v, and then now in space of dy du, we'll have 2u like this, 2u, and then lastly in place of dy dv, we'll have 2v, positive 2v. So this is our Jacobian matrix. So out of this you can still find the determinant of this Jacobian matrix, determinant of the Jacobian matrix. So you know the determinant of a 2 by 2 can be found by multiplying these numbers, subtract this other diagonal line. So 2 times 2 is a 4, and then multiplied by uv minus 2v multiplied by 2u. This is minus 4uv. And then lastly, when you check, it means you have 4uv. Negative multiplied by negative will give us positive. So now we have 4uv.